reminders and such things. This homework 4 should be up on Canvas sometime by tonight. You get 2 weeks for it. It involves no programming. It covers computational learning theory, and you'll be proving things like VC dimensions and pack bounds and sample complexity and such things. Um, if you like more mathy things and more proof-like things, you're going to have a lot of fun. Um, if not, well, it's another homework. Um, the midterms are not yet fully graded. You should expect something by next week. And there's a project milestone that's due today. I know there's been some discussion on Piazza about it, and I've met some people in office hours as well. Um, you need one new submission, at least one new submission. More is okay. And a very short report. It could just be a collection of bullet points, maybe even programmatically generated, about what you've done, what you've observed, any sort of interesting things that you found about the data, about the features, and about the distribution, and what your plan is, how you're going to, what your next two submissions are going to be, at least. Doesn't have to be very long. Just upload a single, a one page, at most a one page document on Canvas. It's mostly to help you plan for things. There's a question. Is it okay if I generate my report as a README file using the same Python code instead of LaTeX? Sure. If you can, you mean a text file, I'm assuming. Yeah, I mean, if you can make it a text file, I don't know if Canvas likes text files when you upload them. So if it does not, upload a PDF, convert it, save it as PDF and upload it. But yeah, um, that should be okay. The important thing is I want you to also write about what you plan to do for at least the next two submissions. I'll be surprised if your code generates it without hard coding that, but whatever works for you. Other questions? Yes.
Are we graded at all on the F1 score we get? Like, is there a certain threshold?
No, there isn't. So that's a question that also came up in other places. So the question is, will the F1 score actually matter for your grade? And the answer is, it depends on what algorithm you use and what F1 score you get. So let's say that you use a certain algorithm. I'm not going to say which one. Let's say you pick one, and you get a surprisingly high F1 score. When I say surprisingly high, I mean much higher than anything that my TAs and I got using that particular algorithm, using those design choices that you have. That suggests something off. So you will actually lose points for that. What I would expect is um, for most of these choices that you'll run, we can easily run them, and we have a sense of what your F1 score should be for that. And you should be within a certain range of that. So if a certain algorithm gives you bad F1 scores, and it turns out that if that algorithm gives everyone a bad F1 score because it's impoverished in some way, that's okay. I care more that you do all the right design choices. For instance, you don't pick hyperparameters out of thin air. You do cross-validation. Your code should not have bugs. You explain your experimental procedure eventually. I mean, you carry out all the right experimental processes. You don't train on the test set, for instance. Um, that's more important to me than getting to the top of the leaderboard. And I know that different algorithms will behave differently. Different feature transformations will behave differently for the same algorithm. So it's okay. On the other hand, having said all that, let's say you choose only bad algorithms. That would be a little odd. So try to get to the top of the leaderboard. You don't have to, but try.
And are we submitting our code at the end at all?
Yes.
We are. Okay.
Yep.
And then is there like a limit on the libraries we can use? I understand we can't use like sklearn.
It's the same. It's the same as your homework.
Okay.
So
I can use a library for like creating folds, for example.
Yeah. Yep. So yeah, absolutely, yes. And you can also, one of those 6 submissions at the end could be from a machine learning library. But for 5 of them, you will need, it's the same rules as the homework.
All 6 have to be different algorithms.
6 combinations of algorithm and feature transformation. So if you run perceptron on the data that we provide and perceptron on a transformed version of the data, those count as separate. Yes.
With the non-one, the non, machine, do you use like the data scalars from standards machines?
Oh yeah. So when you say data scalars, you mean things like normalization and such things, right? Yeah. Yeah. I count that as pre-processing, and it's okay. As long the thing that I would like you to do, though, if you use one of those things, I want you to explain what it does in your report and your motivation for choosing one of those as opposed to another. Yeah. Uh, Follow-up question, I guess, is what do I consider as pre-processing? Um, I've never really been asked that question. Uh, for some reason, I thought uh, basically anything that is not that comes before you send your data to a machine learning library or machine learning code, a learning algorithm, I would count as pre-processing. So this includes um, feature transformations, scaling the features, normalizing them, bucketing the features if necessary, and such things. What is not pre-processing would be um, if your data goes into a machine learning algorithm and then the output gets transformed somehow, that's not pre-processing. So anything that goes into anything that happens to the data before it enters a machine learning algorithm, I would count it as pre-processing. I hope that clarifies things. Other questions? Yes.
So are you saying we're not allowed to augment it after the split process?
What do you mean? Can you give an example?
Like in pre-processing, you're saying like we're allowed to change the features.
Yes.
But then once it's been output by your algorithm, you have to leave it. Or you're allowed to like keep messing with.
What do you want to do to it?
I wonder for like if you try to do like a neural network where you like stitch perceptrons together.
I would count all of those as machine learning. Yeah. So if you stage perceptrons together, each perceptron is the first one that you have is uh, um, the first time it enters perceptron is when the pre-processing stops. Yeah. Yes.
So for our report, is it good enough then to just say like model we chose data pre-processing, hyperparameters for the model, our F1 scores, and then our feature points. That's it.
And any interesting observations you have about the data.
Okay.
Yeah. Yeah, it doesn't, this report does not have to be very elaborate. Keep the elaborate thing for the final report. I think the final report on Canvas, I have turned off the thing that prevents you from seeing what is required for the final report. I think one of you asked me about that at the last lecture. So you can see what I expect in the final report. I want that to be a little bit more formal. This can be more informal. Oh, there are a few questions here. Um, One question is, I noticed some of the attributes have all zeros. Could you override the file to remove those? Uh, you don't need to overwrite the file. You can filter them out when you read the data, and that can take care of it. Another question is, if the pre-processing is what we do to the data before we put it into a machine learning algorithm, how do we submit the file to show that, yeah. So how do we submit a file to show that, given Kaggle wants us to submit a CSV? It suggests that we need to pass in some function after pre-processing to get our predictions. Yes. So after you do your pre-processing, you will send it to your machine. So let me just sketch out sort of a picture here. You have your raw train data, and then you have test, and then you have eval. These are the three data sets that we've provided you. In a perfect world, you'll be doing cross-validation. So this maybe gets split into CV splits. And let's say that you have some pre-processing that you do. And I'm going to use, let's say, this pre-processing. So think of the pre-processing as a function. It's a function that takes your data and produces something that looks like another copy of the data set, except with some scaling or transformations or whatever. So maybe you're trained, so you have the following pipeline. You have some data set that goes into the pre-processing, that then goes into the learner that produces a hypothesis. This whole thing here uh, is internally, your cross-validation will call this process multiple times for each different split. And then on your evaluation, your test set has to go through the same preprocessor that goes into hypothesis and produces labels. And maybe the labels also produces the F1 score for your evaluation. On the eval data, you apply the same preprocessing and use the learned hypothesis, and you get labels that goes into a CSV file that you upload to Kaggle. So preprocessing is something that happens before the learning algorithm sees the data, and the same preprocessing has to be applied to the hypothesis that your learning algorithm produces, because your learner is operating on the preprocessed data, which means it's expecting data that's like the output of the preprocessor. Preprocessing could be, like I said, feature scaling, it could be feature transformations, and so on. And so the thing that you need to submit to Kaggle is this thing here at the very end. And that also reminds me, in your report, I would like to know what F1 Kaggle tells you, and also the F1 that you calculate on the test set. In an ideal world, these two things will be similar to each other. But if they are not, that suggests that something's off somewhere. And it's worth noting that. I hope that this clarifies your question. Are there other questions? Yes.
So you're only training versus training data set and then predicting with testing result, right?
Yes. Yes, absolutely. Yes. Your test, all of this is, all of everything below this line that I'm trying to draw is out of bounds for the learner. And so the training, why is the screen? Give me a second. I'll try to fix this. No, but I think I can't. I apologize for making you wait. This thing is, I can't find my mouse pointer. If you can spot it, help me. You know what? We'll live with this. If something goes below the bottom, I'll try to make sure that I don't write something there. So this is here. Uh, so what I was going to say was this: you will train on the training data. You'll perform cross-validation on splits that are derived from the training data to identify the best hyperparameters, and then train on it. Using those best hyperparameters, you'll train on the entire training data. You'll get a single hypothesis that you'll then evaluate on the test set, and you'll get predictions on the eval set. You'll upload the predictions to the to Kaggle. This is going to be your workflow for no matter what learning algorithm you use. Other questions?
Do we need to calculate for the training result?
You can. I mean, it's not going to. It's something that you can do if you're curious about it. For instance, something that would be interesting is if your training F1 is extremely high and your test F1 is really bad. That suggests overfitting, right? So it's just worth knowing. Okay, let's jump back to where we were. We were talking about boosting and ensembles. On Tuesday, we were looking at this algorithm here called AdaBoost. AdaBoost is this algorithm that creates an ensemble. And the way it works is it assigns a certain weight to each instance in the training set. At the beginning, all examples are equally important. And then you call your, as a subroutine, it internally calls what's called a weak learner. The weak learner produces this hypothesis, in this case, this vertical line here. And based on its errors, the instances are promoted or demoted. The weight importance associated with each example is increased or decreased based on the errors. So these three things are wrong. So for the next iteration, those three examples become more important. At the same time, you also calculate an alpha. This number is the weight, is uh, the score, if you want, or the number of votes assigned to this hypothesis at the final after all the learning is done. And that takes care of one round, and then you do this again and again. So you have now a new weighted set of examples. You find a new hypothesis, H2, which is this line here. You calculate its alpha 2, and then you promote or demote the examples again. You find a new hypothesis based on these that minimizes the weighted error on this thing. You calculate its alpha 3. At the end, the final hypothesis is simply when all the learning is done, a new example comes in. You ask each of these um, uh, experts, if you will, think of this as a committee of 3 members, H1, H2, H3. You ask each of these committee members for their vote on what the label is. Essentially treat it like it's a feature for a higher level classification problem whose weights are alpha assigned to each of these experts. You take the weighted sum, and if the weighted sum is more than 0, then you predict that the label is positive. Otherwise, you predict the label is negative. Concretely, the AdaBoost algorithm looks like this. You keep track of these weights for each example, D. And initially, all the Ds are uniform. So each example gets a weight of 1 over M. These Ds have to add up to 1. You have M examples, so adding up 1 over M times gives you 1. And then you keep iterating for a fixed number of iterations that dictates how many experts that you have. It could be a fixed number of iterations, or it could be some other strategy that you use to decide on when to stop. And we kind of briefly touched upon this on Tuesday. At each step, you find a classifier, HT, that minimizes the weighted classification error. Ideally, it doesn't even have to minimize the weighted classification error. I mean, ideally, you want to minimize it, but in theory, you don't even need to minimize it. All you want is that the weighted classification error should be better than chance. What do I mean by weighted classification error? Every example in the training set is associated with a weight. And we're going to add up all the weights associated with every mistake. And the total penalty, if you will, is the weighted classification error. So the weighted, I'm going to denote that by epsilon t. And now you have a hypothesis ht whose error is epsilon t. You calculate its vote, alpha t, as simply the log of 1 minus epsilon divided by epsilon. You scale it by half for technical reasons. And then you start reweighting these examples. The reweighting scheme is multiplicative. So if an example xi with label yi was incorrectly predicted, that means that y times h will be negative. If y times h is negative, minus alpha times y times h is going to be positive, because alpha is a positive number by construction. E power a positive number is going to be more than 1. That means you are taking your original weights dt of I for that example and multiplying it with a number more than 1. So you're making it more important for the next round. Similarly, if y times h is a positive number, e power minus alpha times a positive number is going to be less than 1. dt times a number less than 1 is going to produce dt plus 1, which is less than 1, less than dt. So you are downweighting the examples that were correctly predicted. Z is simply a normalization term. So every piece of this update here, the choice of the alpha, the way in which the epsilon is decided, and the way in which these examples are promoted and demoted, every piece here is designed so that the Adaboost algorithm comes with a certain theorem, a guarantee of convergence. So these are not arbitrary choices. Eventually, you do this t times. At the end, you have t experts, t capital T hypothesis, which are little h, and t values of alpha. Each hypothesis ht is associated with an alpha t. And then the final hypothesis that you produce is simply the function that takes a new example x and predicts the sign of the sum of alpha times h. The cool thing about Adaboost, and this is where we stopped at the end of the last lecture, is even though your weak classifiers could be weak in terms of their expressive power, like here we have just vertical lines and horizontal lines, the consensus model can have a decision boundary, meaning a separator between the plus and the minus, that does not lie inside the space of your weak classifier. So you've essentially made your final classifier more expressive than any of these intermediate classifiers that you've created. Any questions about all of this stuff? We saw this on Tuesday. I just want to make sure that we are all on the same page before we continue. Question or thumbs up? Okay, thumbs up. 5 thumbs up. Okay. No thumbs down. Okay, so let's move on. Anyone can invent an algorithm and say it's good. The reason Adaboost is interesting is because you can actually prove that it's good in a very specific sense. So it comes with a certain theorem. Suppose you run the Adaboost algorithm for capital T rounds. And we know that each of these, so we'll end up with, after capital T rounds, we'll have capital T hypotheses, each of which has a weighted error of that I'm calling epsilon 1, epsilon 2, all the way to epsilon capital T. And there's an alpha, right? There's alpha 1, alpha capital T. But for the analysis, we're not going to worry about the alpha. So we have every hypothesis, every weak hypothesis that we produced has an error that we can calculate, that we have calculated, because we need to do that in order to reweight the examples. Now, by definition, by construction, the way we chose each of these h little h's is we want the weighted classification error to be better than chance. What does better than chance mean? Each of these epsilons is less than half. Every one of these epsilon is an error, right? Every epsilon is less than half. In fact, if instead of saying it's less than half, so if you have let me plot a number line. This is a 0, this is a 1, a half here. The epsilons can only live somewhere here. Let's say this is epsilon t for some t. That means it's less than a half, which means it must be half minus some positive quantity, right? Let's give that quantity a name. I'm going to call that gamma t. So it's gamma t is a number between 0 and a half. So let every epsilon t be equal to half minus gamma t. Because gamma is a positive number less than half, we know that epsilon t is a number less than half. Did you have a question? Okay. So far, so good. Now so as gamma becomes bigger, what happens to epsilon? You can use this picture picture is below this thing here is gamma. As gamma becomes bigger, what happens to epsilon? becomes smaller. Epsilon becomes smaller, that means you're getting that particular weak classifier has a very low error. Similarly, if gamma becomes large, that means that particular weak classifier is getting worse and worse. In particular, there must be some weak classifier. So now let's just do this one more. Epsilon 1 is half minus gamma 1. This is half minus gamma 2. So we have capital T gammas now, right? There must be one of them that is the highest. The highest gamma corresponds to the worst of these weak classifiers, because larger gamma means, sorry, larger gamma means smaller epsilon. So the highest gamma corresponds to the best of these weak classifiers. So far, so good. So there must be one gamma that's the highest. Let's give that highest gamma a certain name. Let's call that gamma without a subscript. So all the gammas, gamma t's, are between 0 to some number gamma, which is simply the highest of these things. Okay? This is just a setup. Now, the Adabus theorem simply says the final training error of the final classifier, the consensus that you build, right? By taking all these weighted scores of these weak classifiers, is going to be less than e power minus 2 gamma square capital T. What does that mean? So first of all, as capital T keeps increasing, the only two interesting parts here are really the fact that there's a minus here and there's a capital T here. So as capital T increases, e power negative capital T drops down exponentially fast. There are all these scaling factors, 2 and gamma square. It's kind of a curiosity that there's a gamma square. It's okay if the gamma is negative also, but we're not going to worry about that. The final training error drops exponentially fast on the training data. The final error on the training data drops exponentially fast. And that is essentially the key result that comes with this theorem, that comes with this argument. Because gamma t because each epsilon can be written as half minus gamma, what we have is a weak learner. As t increases, the training error drops exponentially, which is amazing. Because then very quickly, you're going to get a model that gets 0 training error, because the training error is simply a fraction of training examples. Eventually, at some point at some capital T, that fraction will become 0, right? Because you only have a finite set. This is actually a very easy to prove theorem. And the proof it's easy but clever. And you can see a pointer on the class website for the proof. I'm not going to walk you through the proof right now, but I really like this proof because it's one of those things where every choice that's made in the algorithm matters for the proof to work. It's almost like these two things fit with each other. So it's a very clever proof that is associated with a very clever algorithm. So if you like that sort of stuff, I would encourage you to work through the proof yourself. What's wrong with this theorem? What's the problem here? Yes.
I would assume that since it converges on the training data very quickly, that you're going to.
That's the question I wanted to ask, and really, that's the problem. Like, is it really sufficient just to bound the training error? What does it mean to get 0 training error? Well, let's not go to overfitting yet. What it means to get 0 training error is that you have a consistent learner, right? You have a consistent learner, at which point the thing to think about is if you have sufficient number of training examples and you have a consistent learner, then you have generalization guarantees. So the question is, how many examples do you need to get generalization guarantees with this algorithm. It's not something you can answer trivially, simply because the choice depends on either the size of the hypothesis space or its VC dimension from what we know from learning theory. And the size of the hypothesis space or the VC dimension depends on two things. The number of steps that you run this algorithm for, because every time you include a new weak learner, weak classifier, your hypothesis space is increasing. You're increasing the complexity of the functions. Remember, with AdaBoost, with 3 weak classifiers, we made a consensus classifier that had these three lines that are overlaid with each other. With 4 of them, you could get 4 lines. So you're building more and you're adding complexity as the number of iterations increases. But it turns out it doesn't matter so much. But the generalization error, uh, provided you don't run it for too long, meaning that capital T does not get very long, you should be okay. I'll give you some examples of this. The training error empirically uh, drops very, very quickly. Here, if the weak classifiers are strictly better than chance, the training error very quickly goes down to something like 0. After, in this case, I don't remember which data this is, but after 15 steps of AdaBoost, the training error goes down to 0. This is the training error of the consensus classifier of capital H final. If you actually look at those weak classifiers, little h, they seem to get worse over time because then they're actually fitting the noise of the data. They're actually doing worse as the number of steps increases. But even more interestingly, the thing that we care about is generalization. We care about the generalization error. The theory tells us that the training error will keep decreasing from the AdaBoost theorem. And the test error, after a certain point, should increase because you're making the model more and more complex. Because you're adding more and more weak classifiers, you're creating a very complex beast. And it should start performing worse. In practice, this doesn't happen. In practice, what we see is after convergence, this is the test error. And this is the train error. After the train error goes to 0, the test error doesn't seem to get worse. And this was a curious observation that was noticed very quickly after the AdaBoost algorithm was invented. And there have been multiple attempts at explaining this. The even more strange thing is sometimes the test error decreases even after the training error has hit 0, which is a little bit of an odd situation. And there's an interesting paper from 1997 that tries to explain this using the concept of margins. Remember margins from the perceptron? It turns out that makes a reappearance here, and there's an attempt to explain that. But it's just more than anything, it's an empirical observation. Okay, quickly wrapping up AdaBoost. It's a simple algorithm. It's not particularly hard to implement. It's rather quick, depending on how efficient your weak learners are. And it introduces only one new hyperparameter, capital T. How many steps do you need this algorithm to run? You can use it with any weak learning algorithm. All we need is that weak learner needs to do slightly better than chance. The caveat is that if your weak learners are too complex, this can overfit quite badly. If your weak learners are too simple, then it can underfit, which means that you might have to run for too many steps to see anything interesting. And really, the performance depends on the choice of the weak learners. A really neat thing that happened around 2005, 2006 was this work by Rich Caruana and his collaborators, where they found that AdaBoost applied to decision stumps. Remember decision stumps, which are decision trees with just one depth. AdaBoost applied with decision stumps is one of the best things to do if you have a small number of features, a few hundred features, like your project, for example. Turns out that that particular learner is not an easy one to beat. And this was done with a lot of, this was purely an empirical result. It was not a theoretical thing. Rich Caruana essentially compared many different learning algorithms on many different data sets, and he found that a consistent winner was boosted decision stubs. This was from 2006. Today, the lessons might be slightly different because it turns out that large neural networks basically do well. At that time, they were harder to train. Today, we have a better understanding of how to train them. Questions? But I think you can think about now you have a new tool for your project. If you implement AdaBoost for your project, you will run into a design question that you'll have to worry about, which is your ID, let's say ID3. Let's say you use ID3. With ID3, you give it a data set, it gives you a tree. That's the first iteration. And then you reweight the examples. You give it the data set. You're hoping to get a different tree. How will that happen if you don't account for the weights? Every example has weights associated with it, right? How will that happen if your ID3 does not account for the weights for each example? So I'll let you think about how to do that. How do you modify ID3 to use these weighted examples? If you have any questions about that, you can come to my office hours and we can talk about it. In fact, I can ask the same question about perceptron. How do you change perceptron so that it accounts for these example importance? You don't have to answer it now. Okay.
Can you couple data boost with any learning algorithm?
That's right. It does not really, it works with any weak learner, except it can fail if your weak learners are too good or if your weak learners are too bad. So there are no guarantees. There's in fact a theorem that we'll not cover in the class, but there's a theorem called the no free lunch theorem. Basically saying that for any learning algorithm, you can create a data set that's adversarial for it. So you never, depending on the data and the task, it may or may not succeed. But it's another tool in your toolbox. I would like to generalize beyond AdaBoost and talk a little bit about ensembles more broadly, where I'll talk about boosting, bagging, and random forests. How many people have heard of random forests? It's something that if you've not heard of it, that's okay. But if I feel like it's one of those things that shows up. I'm like in papers randomly, they'll be like, oh yeah, we use random forests, and they don't explain what, why, anything. It's another ensemble that's actually super easy to implement, and it works with trees, as the name suggests, the forest. And it really does not take too much effort to implement random forests if you have a working ID3 implementation. So let's look at all these things. But more generally, ensembling is a kind of a meta algorithm. It uses a learning algorithm as a subroutine and trains multiple classifiers on the same training data somehow. And at the end, it puts all these classifiers together to come up with a consensus output. And these tend to be empirically quite robust. And I would strongly encourage you to always think of ensembling if you want to deploy some sort of machine learning system. The downside is that you have to train many classifiers. So for more complex learning algorithms, this can be computationally so expensive that it's not worth it. Because imagine, as an example, training one instance of a large language model can take months, just once. If you have to do it 100 times, I think you will burn out the training budget of any reasonable company. And yet, some of the largest models that we have today are actually ensembles, a certain kind of an ensemble called a mixture of experts. So, there are rumors that GPT-4 is a mixture of experts. There are rumors because nobody knows what's inside that box. There are rumors and whispers and leaks that it's actually an ensemble because I don't know why. I mean, it's one of those things that's more robust. I like this example a lot. In 2009, the Netflix had this contest called the Netflix Prize, where they would give you a data set consisting of movies that people certain anonymized data set consisting of movies with for each user did they which movies did they like and which movies did they dislike. I think it was more like a star rating, but let's keep it as like and dislike. So they gave you this big table. The rows are all users, the columns are movies, and some of these cells are do you like or dislike this movie. Most of these cells are empty because thankfully nobody's watched all the movies. Um, and the challenge was they had a certain recommendation system that was essentially for this particular user, will they like this movie or not? And you have to predict that. That's a classification task. And they had an internal system that they were using around that time. And the Netflix price challenge was, can you do better than our internal system? If you do that, you get $1 million. And anyone who was doing machine learning at that time decided to try their luck at this. And it turned out that it was really, really hard to beat the internal Netflix system. Eventually, the team that won the $1 million was actually, the name of the team was the Ensembles. Um, the Ensembles was actually an ensemble of two different teams. They just took their existing systems and combined them. If memory serves me right, if you look at those two different teams, they themselves were internally using ensembles. It was eventually, I think the $1 million was shared across like 10 people or something. Still not a bad deal if you're a student. Um, but this is just an anecdote, the ensembling. And eventually, I think that big ensembles did slightly better than Netflix's internal system. I don't know if they actually used it eventually, but it's a nice story. And I don't know how much of the story is true. Yeah, you can look it up. So we've seen one ensemble, which is boosting. Boosting is the idea of boosting is you assign equal weights to all the examples initially, and then in each iteration you train a model on this weighted training set. You compute the weighted error, and then you increase the weights for the examples that were where the previous classifier made a mistake, and otherwise you decrease the weight, and you combine all these weighted classifiers, and you may have to run like hundreds of these steps. You might have to train hundreds of weak classifiers to make any progress. The final model is this sort of a carefully scaled consensus of all these hundreds of weak classifiers. There are different boosting has there's been a lot of analysis of boosting, in particular AdaBoost. There's some analysis that says that it tries to maximize margin in a certain sense. There's connections to logistic regression. You can follow up these references if you want to read these papers. Yes.
Just had a random thought looking at that iteration step where we are increasing the weighting for the cases the model gets wrong. That says to me that boosting is mistake-driven learning algorithm. Is that the case?
No, it's not. It's not mistake-driven because in the strict definition of mistake-driven, you're operating at one example at the scale of one example at a time. Here you're operating at the level of entire data sets, right? And the second thing is that you have all the labels up front. It's not online at all. Yeah. There's a question on Zoom. Where does the ADA part of AdaBoost come from? What is ADA? I think I don't remember. Actually, I don't know. I think it's adaptive. I think it's adaptive because it adaptively changes the weighted errors, the importance of examples on the as we go along. I think it has to do with that, but if you find out, let me know. Okay, so this was the more AdaBoost and boosting is one of the more complicated instances of ensembling. The other ensembles that we'll discuss are very, very simple. There's something called bagging. Bagging is short for bootstrap aggregation or aggregation. It was invented by Leo Breiman, who is a statistician, and it's a very, very simple algorithm. Imagine that you have some learning algorithm that can produce a classifier C. It takes a data set and produces a classifier. you don't have to, it's a black box for you. You don't have to do anything to that learning algorithm. It's something that you don't even have to look into. What you do is you have a training set. This doesn't have to be M. This could be any number M. Yeah, and you repeat multiple times, T times or N times. At each step, you draw samples from the training data with replacement. Okay? And you construct a certain number of samples, M prime samples from the training data with replacement. The with replacement part is important. Sampling with replacement is also called bootstrap aggregation or bootstrapping. Bootstrapping is this process where you have a set and you're sampling that set with replacement. So if you have 10 examples, maybe you draw example number 1 the first time, and then 2, and then 1 again, and then 3 again. Maybe this is your need. You construct this set here. So some examples can get repeated. This looks like a training set. I mean, this looks like a list of numbers, but that set that you've created looks like a training set. It's a set of examples, right? Give it to any learning algorithm you want, and you get a classifier. In the tth iteration, you get C sub t. You do this many times, and you get many classifiers. Importantly, because each classifier is trained on a different sample of the data set, they're not all going to be the same classifier because you're randomly sampling the examples. You get as many classifiers as the number of rounds you've run this, and that's it. Learning's done. At prediction time, when a new example comes in, you ask all of these classifiers for their label, and you basically each classifier votes on the label, and you take the label that has the highest number of votes. It's a method for the underlying technical component here is the sampling with replacement or bootstrapping. So the process of sampling data, training data with replacement helps you generate multiple different versions of your predictor. And by averaging them, you essentially get a robust consensus model. And you can either do, if you have regression, you can average the final label. If you're doing classification, you can take the voted, you can each of your classifiers can vote on the label, and you take the one with the highest number of votes. Each subsample of the data that you create is called a bootstrap replicate. And that's why the name for this method is bootstrap aggregating. Or nobody calls it bootstrap aggregating, it's called bagging. Turns out bagging is very robust. With decision trees, bagging gives surprisingly good results. And it's so easy to implement because all you have to do is just implement this sampling with replacement. You don't have to implement sampling with replacement. NumPy does it for you. So you can just sample your data set with replacement, train a tree, and keep doing it as many times as you want. And it turns out that it can actually give good improvement, and it makes your final predictor fairly robust. So what you have now is another tool in your toolbox. You don't feel like implementing boosting with all those careful weighting schemes and all that. Just use NumPy sample with replacement and keep training a bunch of classifiers and aggregate them. And Leo Breiman tells you that it works. The one place where it might increase the predictive capability a lot is if just slightly perturbing the training data can wildly change the prediction, then bagging can help improve performance because essentially it's averaging out across those variations. So those are the kinds of data sets where bagging might help the most. Upfront, looking at a data set, you don't know if you're in that situation, but you can always run bagging. So here's an example of how you might do bagging. So let's say with decision trees, and here I'm showing an example of decision tree with regression where every leaf node is a number. you, let's say you've decided to create capital T trees. So you create T different bootstrap samples of the data, and you train those many trees. And when new example comes in, sometimes they're called out of bag samples. That's from the statistics literature. When a new example comes in, you ask each of these trees for the label. So this one predicts 0.23 and this one predicts 0.31. And you just average all of them and you get a final label. That's basically it. Any questions? So there's a question. How do decision stumps do with bagging? Is it possible, or is every stump going to be the same because of replacements? Not really. Actually, this is something that's worth trying. Um, Decision stumps with you want your trees to be not very large. So decision stumps are better than fully grown trees for bagging. It's entirely possible that many of the stumps are going to be the same, but not necessarily all of them. If you have 100 features and you do bootstrap replicates of the data, the thing that the decision tree does at each step is the decision tree learner does is it picks a certain feature to split on. It does not necessarily need to always pick the same feature because these bootstrap replicates are going to be different. That's going to change your information gain, etc. And so it might pick different features at each step. And so there's no guarantee that all your trees are going to be different from each other, but there's also no necessity that all your trees are going to be the same. I hope that clarifies things. Yes.
For this, the capital T, like the number of samples being took, is that like, does that have the same relation as we saw in data?
Yes, basically, it has a similar sort of effect. As that number increases, you might end up overfitting a bit. But in this case, it's slightly different. Oh, actually, no, it's in the same flavor, but it's not the same. Because here, as the number T increases, you're getting more and more bootstrap samples of the data. So it might actually increase the robustness of your predictor doing that. So there's a trade-off, but the trade-off is more computational. Are you willing to spend the time doing that work? But it's also possible that by doing that, you might end up overfitting the data a little bit. But this is an empirical question, just as always. Yes.
For this valuing thing, we also have to make like the weight, like some of the weight equal to.
There are no weights here.
Like
No, those are the predictions of the examples.
Oh.
This is a regression tree. So each tree is predicting a certain number here. I'm just using a regression tree mostly to confuse you. Because trees can also be used for regression. We never really talked about that. But this is the prediction of the first tree. This is the prediction. We never have any weights in this. We just have a collection of trees and we ask all of them what's the label and pick the most common label if it's a classification. That's pretty much it. Okay, so what's the key thing about bagging? I was basically randomizing the data set with bootstrap replicates. I could throw in a little bit more randomization. And one way of thinking, one extension to this is something called random forest. Excuse me. At each step, you do the same thing as bagging at the beginning. You create possibly thousands of bootstrap samples of the data, and you train a tree. Random forests is, because it's called forest, you're collecting trees. You train a tree. But at each step, in addition to just taking the bootstrap replicate, you also subsample the features that are allowed to be used for each bootstrap replicate. So maybe for the first tree, you only use features 1 to 10. For the second one, you use features 20 to 100. You random, and this is a randomly chosen set. It need not be 1 to 10. And you do that separately for each, independently for each tree. So each tree ends up, in some sense, having a different view of the data. And then you aggregate the same thing, and it's basically the same. Rest of it is the same. This is a random forest. And random forests are a very good uh, sort of if you don't really know much about the problem, you don't want to think too hard about it. The kind of things that you might throw at it are random forests, because there's not much thinking going on here. Right? You just need to pick. You have only two hyperparameters. How many trees do you train? And how many features do you sample? Or what fraction of the features do you sample? And this gives you a little bit more robustness. Questions? Do we want each tree to have the same number of features sampled? In practice, I would not do it that way. There are different choices here. You could choose the same number of features at each step, or you could have a single probability that any feature is sampled, and you toss a coin for each feature and ask whether it should be present or not. So it may not be the same number, but going to be the similar sort of a number in expectation. These are all kind of used, and I don't know which of these works better in practice, because I've seen both of these, and it's not clear necessarily. Yes.
Do we only perform a single sample on each tree out of the set of T trees?
What do you mean?
Like, so we draw T number of bootstrap samples of each data. And then do we only do a single
No,
sample?
for each bootstrap sample, you choose a different subset of the features.
Okay. I'm just wondering, do you do that drawing of subset of features multiple times on each tree?
No, just once.
Just once, okay.
Yeah. Other questions? This brings us to the end of our lecture on ensembles. We've seen what is boosting. And I started this with a question on learning theory. Does weak learnability imply strong learnability? If you have something that is provably only weakly learnable, does this mean there exists? Does this mean that concept is learnable in the strong pack sets? And the answer is yes. And the proof is this algorithm called AdaBoost that does this whole thing of weighting each example and such things. You should know what the AdaBoost algorithm is, why it works, and so on, and just the mechanics of it. But more generally, we talked about this idea of ensembling, and ensembling is an important tool in your toolkit. There are different kinds of ensembles. We only looked at 3 of them. You could do other things also. We looked at boosting, bagging, and random forest, but there are other ensembles. Here's an idea that's kind of super easy to implement, super easy to conceive of, a little bit more messy to implement. Imagine that you do this bagging style idea where you train thousands of trees, either maybe on bootstrap replicates, or maybe you just randomly, with or without replacement, it doesn't have to be one or the other. You have thousands of trees somehow, thousands of different trees, possibly different trees. Now, rather than just having them all vote on the final label, you could think of each of those trees as a feature transformation that applies to the training data. So you take the tree each tree, you apply it on each example, and you get a set of labels. Now, rather than treating those as labels, you can use those labels as features for a perceptron. So you have a bunch of trees. Let's take only 3 of them, T1 of X, T2 of X, and T3 of X. I've trained these 3 trees. I find myself in a position where I say 3 trees quite often. Let's make it 4. 4 trees. You train 4 trees on different subsets of the data. Each of these trees produces a +1 or a -1. That means I have an example X. I have a way of converting that example from the original feature space into a plus in the space of these trees. So I have 4 trees. I have 4 labels, plus or minus. this can be seen as a feature vector. And I can train perceptron on top of that on the training data. And that's an ensemble. I have an ensemble of trees where each tree is given a weight that's coming from perceptron. And there's also a bias feature because you're using perceptron. That's another ensemble. So there are other sort of easy ways of combining these classifiers. If you, when we come to probabilistic models, if your models predict probabilities, then you can train multiple of these and combine them by just multiplying those probabilities. And that's something called a mixture of experts. So ensemblings, the different strategies for ensembling keeps getting invented all the time, and they all have a similar sort of a flavor. We have these sub-classifiers, a collection of them, and there's some way of combining them. Combining could be very simple, like voting or just averaging. Combining could be more complex, like what we saw in AdaBoost, or this thing here where we have trees that are getting combined with a perceptron, or it could involve multiplying the predictions, which are probabilities, and so on. But the philosophy is essentially the same. One classifier might overfit the data or might not be expressive enough to model the problem, but a collection of them together might end up being more robust and actually might also increase the expressive power. Practically, from your project point of view, now for every learning algorithm that we look at, you can also start ensembling them, and now you can start mixing and matching. You have many, many different learning algorithms right now. You can even think of ensembles, but I don't know why you would do that. Questions?
Actually works with new learners, right? And what if our like
So the question is, this only works with weak learners. What if your underlying learner was very good? I have two answers there. First one is, if your underlying algorithm is very good, why do you need to do better? Alternatively, let's say your underlying algorithm is very strong. It's not perfect, but it's very strong, and you want to get a little bit of a boost on top of that. Then it depends on the difficulty of the problem you have and the amount of data that you have. If the underlying task is very difficult, then you might still get an improvement by ensembling. Like I said, with as recently as um, the big GPT class models, their underlying models that they are ensembling are essentially like GPT-3 or 3.5, and they are ensembling that 8 to 15 times. And the reason that it does better is because the problem they are trying to solve is so much harder that even a very strong classifier is not that strong because the problem is tough. So it depends on the difficulty of the task.